based on time, as I put the pack together, I've left the Airborne than the title might suggest. We work in both Subsea and Airborne, but I've literally only a slide or two in the Airborne. So the talk will focus more on the Subsea robotics for renewable, but we are active in both areas. So briefly, what I'm going to try and squeeze into the talk is introduction to the team, a look at ocean and Ireland. I think it's a bit of a no-brainer, so I only say it there. I don't really go through it in any more detail. We look at energy, renewable energy, and renewable. It's one of the grand challenges. We need to reduce our carbon emissions, maybe reverse climate change, but one of the main aspects of this is obviously dealing with energy and renewable energy. We look at how big the potential sector that the robotics we develop service and how big it will be in the future. And then we'll start to focus in on some of the challenges of ocean operations with ROVs. I look at some of our marine robot technology and then some video clips and examples. Okay, the team, here we are, that's me in top right. There's 4 academics and 5 academics, about the same number of postdoc research associates, and then the rest are PhDs and research assistants. So I won't go naming them all, but we work in marine robotics, airborne systems, and mostly field robotics, and mostly with a focus on the ocean. Our funding, so the centre is based within the Department of Electronic and Computer Engineering here at the university. Our funding is significantly from SFI. This marine robotics or field robotics is largely funded through MARI, the Centre for Marine and Renewable Energy, of which I'm a co-PI. So that centre is led out of Cork, but there's 9 industry partners, and Technical University of Dublin is joining it for a second phase, but I'm a co-PI and lead the activity here in Limerick. We also do robotics in the manufacturing space and then on the software side. So, but because I'm focusing in on the marine robotics, I'm giving MARI a bigger emblem here. Our funding then also comes from Irish agencies and programs and EU H2020 funding, etc. Okay, offshore wind. Well, offshore marine renewable energy is the area we are developing technology to service, but the commercial one between wave, wind and tidal, the commercial one is wind. So just to give you some idea on this sector, the number of areas zoned around UK in round 3, they're going further offshore, more remote, and very large amounts of energy. Offshore renewable capacity will be installed and is currently being installed. So servicing that technology, inspecting, repairing, maintaining those devices, surveying the sites where you put them, etc. That's where we use the robotics. In the Irish case, based on the studies done by SEAI, etc., we have in some ways even stronger winds. So some of the best wind resources in Europe and around the world are off the northwest coast of Ireland, west coast of Scotland, and up the northeast Atlantic, the west coast of the continent. But in many ways it's even more challenging. So, and our population is smaller, so we don't have the same scale rolled out. We don't have any really rolled out on the west coast, but we certainly do have some on the east coast. In recent times, UK is investing very significantly in offshore wind. Other countries as well, as indicated here. And an example of an offshore wind field. And when you look at a global map of the world, you see where the wind resource is. So the northern latitudes up in our temperate zones get some of the best wind resource. In the southern hemisphere, there's a mirror image, but it's mostly in the roaring 40s. There ain't much population down there. So most of the zones that offshore wind is being deployed is northwest Europe, off China, and US, North America. US and Canada. Okay, so just looking in at some of the areas that are zoned. So the inner little areas are already operational. We have an Arklobank wind farm, and you see there's Germany, Denmark, is also investing very significantly in offshore wind. An International Energy Agency data here, so based on that web link if you want to follow. So you see where we roughly are here in terms of the capacity and where they're projecting this will go. So the idea is we'll have, if we want to overcome the carbon problem and maybe reverse and arrest climate change, we need to replace fossil fuel use for generation of energy and electricity by renewable. So for example, the largest offshore site just commissioned, the Walney extension, is where the X is in this map. So that's between Morecambe Bay and the Isle of Man. Our team worked on some survey work on a close by wind farm. Okay, working offshore, this image is sort of gives you, so this is courtesy of Siemens, but it can be a harsh environment and also an expensive environment. So installing and constructing these devices out in that ocean can be challenging, but also if servicing, every time you have a technical problem, if we have to scramble helicopters or ships, it can be very expensive. So compared to onshore wind, if there's a technical problem, you can have an engineer up servicing it the same day. Offshore wind, if you cannot deal with the same servicing, you potentially have very expensive plant downtime. Okay, so a lot of the focus is operation support engineering, so research enabling operations in the harsh marine, wind, wave and current regimes. So within MARI we're funded to do this support and engineering development for renewable energy, be that wave, wind and tidal. Wave and tidal aren't really commercial, but wind and offshore wind is very much commercial. But just a little look at wave. Some of the challenges are tidal energy. So tidal energies, you'll obviously be choosing locations with a very strong current. Most ROVs can't operate in these very strong currents. So for example, like 1 meter per second is close to 2 knots. So with these flow rates at this Maygen site, in fact the ROVs cannot operate except close to tide turn. So many hours in the day, if you get two tides per day, there's only narrow, maybe 1 or 2 hour windows where you can do the engineering work. So that gives you an indication of some of the challenges. Okay, ROVs. I'd say most of you maybe are familiar with ROVs to some extent from TV, from the David Attenborough type programs, but in many ways when you see underwater world, you see the image from the camera, you don't actually see the vehicle itself. So this is typically an ROV deployed in offshore oil and gas infrastructure, might be turning valves, it might be involved in construction, etc. And they're used for inspection, repair and maintenance. But in reality, the technology is similar to, it's human in the loop. The human is based on video through the cameras and through sonar imagery, flying the ROV, manually piloting the ROV and manually controlling the robot arms. In the challenging conditions of offshore wind, is that sufficient? That's the question. So robotics in ocean energy has been used for a very long time in the offshore oil and gas sector. For the marine renewable energy sector, we have to operate in strong currents, strong winds and high energy wave environments. So to some extent, this new sector gives unique challenges for the ROVs, and that's really what we're focusing on solving in a lot of this research. So a very quick look down through some potential ROV tasks. You might use ROVs for high resolution survey, sonar, laser or photogrammetry, mapping of the seabed or imaging the structures on the seabed. You use them during the construction, working with surface vessels and barges in the heavy construction, maybe working on moorings, laying pipelines, foundations, the rock armour around the base of wind turbines, touchdown support. So if you've large barges laying large civil structures, you may have the ROVs as eyes on the ground, if you wish, on the seabed in touchdown support. trenching for cables, salvage, cutting up wrecks that, on navigation channels or whatever. One of our support companies is the third biggest salver in the US. Pipeline and cable inspection, general visual inspection, laser imaging, manipulator work. Most of the manipulators and stuff is hydraulic, so it's a bit like the backhoe on your excavator. They're hydraulic devices which are operated by pilots operating levers. Valve turning, probing to check the anodes on the structure, the sacrificial anodes, so that the steel structure isn't dissolving into the ocean. Removing biofouling off the structures, inspecting the grouts between the main wind tower and the foundation structures. Blowout preventers, so in the oil and gas, especially after the deep horizon, it's now mandated that the ROVs in drilling ops have to have the power so that they can manually operate the blowout preventer in case there's a fault in the systems. So it's a backup system, fail-safe backup. Drilling touchdown support, these are the types of things. So in many ways, ROVs are the workhorse of the subsea environment. As we move into the supporting the renewable and the offshore wind, we're going to be operating in zones with high wind, otherwise we wouldn't put the turbines out there. High wind generates waves, so we're going to be in waves, wind, so we're in the splash zone. We're in relatively shallow water. In the oil and gas, even when it's wavy, they punch through the splash zone to go down to relatively quiescent water below. So we want to be able to do these tasks such as inspect, cleaning, cutting nets, cable mating, etc. So we want to move away from this origin. So if you just use the oil and gas technology, they're designed for very low sea states, ops, and very low currents. So we cannot come far away from this origin. We wish to be able to extend how far away from the origin we can go, because otherwise we have to wait for the one calm day. If you're offshore on a productive wind farm in a location with very high winds, you could be waiting a month for a suitable day with the winds below on the Beaufort scale at a level that you can operate. So we're trying to develop technology to extend the operation capability of these robot systems. We're not saying we can go all the way. We're not telling people we'll get you up to 10 knots or whatever, but we're saying if we can extend the operating capability, we're extending the window of opportunity. If we extend the window of opportunity, we can do the work for a larger fraction of the time and make, so that's really the focus. As far away from the origin as we can move in that. As somebody pointed out, when we talk about the airborne inspection part, we really need more axes, and we begin not to be able to fit this diagram on a 3D plot like that, but we want the airborne systems also to be able to operate in the remote. So our ROV, so this is the type of environment and infrastructure we want to work on. Offshore wind, wave energy devices. We want the robots needed above and below the water for inspection and intervention. And because of the conditions, we're going to need significant, DP stands for dynamic positioning, a capability to hold station relative to the target, or the operators simply will not be able to achieve their tasks. So what I want to focus in on now is conventional ROV technology versus what we've been developing. So as I said, the ROV technology in many ways is quite like a backhoe excavator. So it's very reliant on pilot capability. So the piloting is manual, flying the ROV forward, back, based on heading and depth instruments. So it's very pilot skill dependent. If you wish to fly a ROV to follow a pipeline or to a target, we want to develop the capability so we can fly these ROVs in significant disturbance with high waves and currents. So we still want human in the loop for the safety critical part of the operation, but we want the autopilot system so that the robots can operate and the pilots can operate without having to manually react to the disturbance from the waves and the tide, etc. It's a bit like little small Cessna aircraft, the pilot flies completely manually. Fighter aircraft, unless you have the automatic computer auto-piloting controls, the pilot will not be able to fly a modern fighter aircraft. And so it's really, we are suggesting it's the same with operating ROVs in this highly disturbed environment. So low-level controls, ROVs are generally factory-tuned and set And then when you bring them into field, you might change the payload, you might add instruments, you might take off instruments, swap out the manipulators, etc. So to some extent, the factory-tuned low-level controllers are almost, by definition, they're not very well tuned. One of our good members here, Ed Omerdick, has developed automatic tuning of controllers, so we can actually fully automatically control those controllers on the fly in the field. So that's important because it gives us good response of the vehicle. Faults, effectively on the ROV systems, you will have alarms, etc. And if you get an alarm with a fault in its thrust rigs or the like, you recover. Again, we've developed a capability for thruster fault detect, isolate a given thruster, accommodate that fault by redistributing the thrust, for example, to the available thrusters and continue. So this allowed us to keep the operation windows open even in the conditions of a fault. Manipulator technology, it's slave arm method of operation. So the pilot, a bit like using a digger on a backhoe, is based on what they see in the trench they wish to dig. They're manipulating the valve controls through the hydraulic cylinders to get the straight line. If we're on a disturbed robot addressing a maybe heaving target, that's simply not good enough. So we've implemented inverse kinematic engines and visual servoing, so we have automatic vision in the control systems. So trajectory following, again, it's with conventional ROVs, it's down to pilot trial and error without precision nav. So if you wish somebody to follow a given line based on their planned position indicator or follow a pipeline, they'll be overcompensating as they go a little bit off, a little bit back again. We've got full 6 degrees of freedom precision flight control, so we can plan the trajectories and automatically fly such a thing with human supervision. Image processing in real-time 3D model generation, that's not available in commercial ROVs. What we use that, have developed it for and use it for, is real-time image processing, which unlocks our image-based flight control. So this is especially important when our target is in motion. If the target is moving, if we can image the target, we can get the robot to motion match or at least become fully cognizant and aware of the motion of the target and so intervene on a moving target. Resident robotics, this is actually a big development area, so there are many people working in this area developing resident robotics. So if you have very large infrastructure offshore, developing robots that are permanently based out offshore. So we're also doing some work in this area, working on secure intercontinental comms, so we can fly a robot with a pilot, hundreds of thousands of miles away. Remote comms for real-time international pilot remote. So we'll show some of that in the video clips. And automatic docking, and etc. So I've shown this diagram before, but effectively the summary point, the marine renewable energy ROVs need auto and semi-auto pilot. They need dynamic positioning to unlock relative to target flight control. And we call that blended autonomy because of the safety critical aspects, because of the insurance aspects. They won't allow us to fully automate these robots. They won't allow fully automatic robots work on the valves and on the deep water oil wells or whatever. It's a bit like you could fully automate cars, but you won't get insured. We're still going to need people behind the wheel. So working in the splash zone is where we're going to be for offshore wind. MRE operation support, inspection intervention capabilities. So we're working in the waves and maybe tidal flows. ROVs and targets are potentially in motion, especially if we're going for floating offshore wind, which is the new development as they go into deeper waters. High turbidity, so significant waves churning up the seabed, significant bubble entrainment within the water column. Complex lighting, so you're getting lighting effects which affect your video. It can be do an image processing on a static target. Your AI-based vision system may be fairly stable. As soon as you put it underwater with the variable lighting, it becomes very much more challenging. Anyway. Okay, what approaches to ROV ops must we achieve? So we want to detect the images, targets and environment in real time. So our focus, if we want to be able to control the flight of the ROV, we need to be able to do our image processing in real time. Piloted systems, so pilot in the loop will be overwhelmed as the sea state conditions get too significant, too disturbed. Fully autonomous systems, potentially also maybe get overwhelmed, and for insurance and those sort of reasons, maybe even if you have the capability, they likely will not allow robots to operate fully autonomously. So we need auto-assisted pilot-in-the-loop solutions. So we've sort of coined the phrase blended autonomy. So we want to blend the human in the loop with the autonomous system. So precision inertial solutions alone will not work unless we could put precision inertial navigation on the ROV, and we do have it on the ROV, but we need it on every target object as well, so that we know the motion of the target to centimetre accuracy as well as the ROV. So that's not a solution. We can't stick a 100K fibre gyro instrument on every target. So we want precision nav. We want to unlock image-based target reference flight control. What's this one now? So we want to be doing real-time control system relative to target imaging in real time. So we want real-time fusion of, we know their engineered structures, we know the geometry of the table, we can have the CAD models of the table, we can have images from camera of the table, we can register the image from camera with the known geometry, so we can register the position of, if I'm the robot relative to the table, the position of the robot relative to the target. So that's the sort of thing we're trying to unlock. Then we can use that for motion detection, and if the table is heaving in an ocean, I could even try to match the motion. It's these types of, so they're basically our research objectives. So now we'll go into some examples. So again, there are actually, I started off with 200 slides in this, and I was crushing down the slides into the deck I have. We've many examples of this, and you see a lot of this online. So I just want to give you a flavour. We end up with real-time models of the robot, and a virtual model, and the physical robot is twinned to a virtual instance of the same robot. So as the ship is sailing and pitching and rolling are moving in 6 degrees of freedom, so X, Y, Z, and also rolling, pitching and yawing, the model of the ship is slaved to the real ship. The model of the robot in the water column is slaved to the motion of the real ROV. We've imported the seabed, so we can effectively, from the ROV camera on a submerged ROV, you can maybe see 1 or 2 meters, depending on the turbidity. We can make the ocean transparent, so the pilot, the master on the ship, or the ROV pilot, or any other people involved in the operations can get a 3D view of where everything is relative to everything else. So we developed the pilot interfaces. Top-down 2D display is still necessary and very useful for planning and operating your survey, but the 3D view is also very useful. So this is again under development, and I think my colleague Ed Umberdick will give presentations with much more emphasis on this. So I have only 1 or 2 slides. So for example, at the moment in the updated version we're developing like a gaming engine sort of version of the same thing. So we are based with our larger robot in Limerick Docks. So this is a model of Limerick Docks, although that's a model of the older robot. So you can fly it above the waterline, below the waterline in this transparent dock. The dock in Limerick is about the consistency of Guinness. You cannot see a camera on one robot arm, you cannot see the other robot arm. But in this transparent dock, we have full visibility. So if the position and the real-time motion of the robot is good, well then keeping track of where the robot is relative to a target you can't even see is possible. So for example, it'd be like landing an aircraft on the deck of a ship at night in fog. We don't need to see. So this is a deployment of a robot we built and developed in our own centre in the Shannon Estuary. So we have 1 or 2 knots of running riverine flow. We were in an emergency response exercise searching for lost cargo from a ship that went aground. So this is the virtual image in the older version. This is the forward-looking sonar. We've detected the shadow from a target, and so that's likely our target. And here we are getting the robot to fly semicircles around the identified target so that we can survey the target in the 1.5 meter flow of the river at the time of that operation. So to get a pilot to manually fly the robot around the target in a 1.5 meter flow, it's just simply not possible. Okay, so manipulator controls. We've done a significant amount of work here. Now the manipulator control aspects in this research, control approaches have been used in industrial robotics for many, many years. But field robots such as, right, so this is conventional ROV with manipulators. The human pilots the ROV, and we'll see in a moment, this is how the pilot moves the manipulator based on the video feedback. So that's effective, but not so effective if the target is moving or if you're in a more challenging, complicated environment. So what we wish to do is develop a full inverse kinematic engine, so we get the same inverse kinematic control as we have in industrial robotics. And then we want to put vision systems and sonar imaging systems in the loop, so mount cameras on the robot arm, and then get the robot to automatically maybe follow or interact with the targets. So such solutions exist in manufacturing for many, many years, but they don't exist subsea. So we started with doing some of this visual serving, aligning up on targets with industrial robots, and then implement this on the hydraulic manipulators. So this is a hydraulic manipulator and implemented in a kinematic engine, so we can control the motion of that manipulator in X, Y, Z orientation about any point in space, etc. So it's implementing what already exists in industrial robotics on subsea robotics. So here's some examples. We're operating just with the inverse kinematic engine to clear a rope out of the way of a target, so we can then try automatic visual servoing on the target. So most of our work we do in dry lab, early testing in wet lab, underwater, we do some testing, and then offshore, so in tanks and then offshore in the field. So this is some trials offshore with an ROV manipulator, in this case on a static robot addressing a target. So it's a valve T-bar as typical on an offshore sub-plant. And we're using fiducial markers here because parallel researcher was developing the real-time imaging for real targets. Then the other thing, if you automatic motion of your robot manipulators, we want to be automatically checking for collision and interference between the manipulators and between the robot arms and the structure. So again, that's a version of that. Okay, so real-time image processing in robot controls. So that we can unlock this target reference, flight control, etc. So again, there's a PhD finished up in this area who worked on the development and testing of state-of-the-art 2D and 3D feature-based systems. So development of a direct, dense 3D method. So there are many groups that offer what they call 3D photogrammetry. So for example, you can mount a camera on a UAV, you can fly around the campus, image the whole campus, and based on the motion and maybe with stereo cameras on the UAV, with the two cameras you can get stereo vision, so you get a slightly different angle view. From that you can regenerate the 3D topography of the campus, for example. But most of those services are offered offline. So you acquire your video, you send it to one of these people who number crunch it for hours and hours and hours and hours, and they eventually give you back the 3D model. If we want it to be useful in flight control relative to moving targets, we have to be able to solve that 3D geometry from camera in real time. So this PhD student is getting that 3D image processing up to 30 hertz. So he's able to regenerate, which is frame rate from video. So unless you can approach the frame rate of video, you cannot do it in real time. If you cannot do it in real time, you cannot use it in your flight control loop within the robot. So this is an example of doing it in air. We're using the Kinect system, so it's a camera and it's an infrared camera also. So you projected structured light in the infrared, which isn't visible, but from that you can generate the 3D geometry of the target. And the next image then shows, this looks identical, it looks like a camera image, but it's not. This is the 3D model of that target. So this is a poster. We can see the resolution because we can read the poster. It's a small little mini ROV, it's a computer bag or whatever it is, the side of a computer casing. So if we build up a model in real time of such a target, we could get the robot or the robot manipulation to pick up the cable or to turn on the computer or that's what we're trying to achieve. So this is an underwater test site we have up near Lough Derg in Portroe. There's a quarry and it's a dive training centre, and it's used, so they've installed a bar so that the divers go off down and sort of have a beer. I don't know how the hell they drink the beer, but this again looks like a photograph of the scene, but this isn't a photograph. This is the 3D model of the scene after acquired and generated by the so now we're manipulating this 3D model, so we can see the mannequin, we can see the bar. We didn't image the bottom of the stool legs, so they're not part of the model. We didn't image the back of the mannequin, so she's not complete. But if you zoom in, maybe in this projector you can't see it, but the resolution is good enough to read Guinness on the Guinness sign. There's a tin of Guinness somewhere on the bar. I think on this projector the full resolution isn't available. But the idea is we're building up this 3D model of the world from our cameras, and we're able to then use that for flight control of the robots. And we're doing the same with sonar, because one of the challenges underwater is the turbidity, such as in Limerick docks, means sometimes you cannot see even 2 inches beyond your nose in very turbid waters. So this is the real-time image processing. That's a boat on the bottom of that flooded slate quarry up in County Tipperary. This is the actual video. This is the real-time 3D point cloud being generated on the fly. So we're building the 3D geometry from the camera passing by the target. Okay, resident robots, another area we're working in. If we're deploying multiple like in some of the wind farms that are going off, the one that's planned to go off the Irish coast up near Carlingford had something like 58 turbines, 58 or 55 by 6 megawatt turbines. So very large infrastructure, very large investment. So one of the approaches, we might deploy robots in and out on service vessels, or we might permanently deploy robots on the seabed. So that's what the resident robotics is aimed at. So in order to do that, we want to be able to remotely control these robots. So one of the areas we're working on is, even on legacy systems, we wish to get security. We want to control these systems over the internet. So we're putting bump in the wire technology. So with this bump in the wire technology, we can, this may be shown better on the next slide. So with a small device inserted at the pilot, the human pilot control station, and maybe remotely in the field, we get secure communications in between. So we can communicate between the two through the internet, but it's secure comms. And we've also we want to do the latency measurement, so we know the latency and the time delay, because if we're real-time flight controlling, we want to be able to measure and guarantee the latency. So this video clip, if it ought, long endurance remote, so it basically tells you what we're trying to do. The following video shows possible applications of this technology. I can actually advance this video. So for example, you have a model, that's what the pilot might see. Now let's see where the pilot is. We were hawking this and pitching it to sheikhs who turned up at Oceanology and see would they give us some money, but they didn't. If they wanted to invest in offshore wind off Ireland. So for example, so this is a graphic to get the concept across. I don't think we'd have a little mini robot that close to the waterline, because the winter storms would break it apart. The robot might be permanently deployed subsea. But anyway, the concept is still valid. Then the next video shows us actually remotely controlling a mini robot in our tank. And again, we've done this, and Dino, for example, has flown this little mini ROV, taken it off a hook in our tank while he's piloting it through the internet. So video being sent all the way to, we've done it from Newfoundland, we've done it from London, we've done it from Dubai, we've done it from Italy and from Croatia, demonstrating the remote control of robots from intercontinental ranges. Fly around the tank, and this is a low-tech little mini ROV. It doesn't have sophisticated auto controls, so in order to get it back on the hook, the latency has to be of the order that the human pilot actions mean you can get it back in the hook. So if we get to the end of the video, we'll see Dino get it back on the hook. Maybe I'll skip ahead. Here we go, he's approaching the hook. So that tank is in our lab here at UL, but Dino, I'm not sure which trial this was, but it might have been Italy or Dubai or somewhere. Anyway. It's worth seeing, does he get back on the hook, just to see, are we bluffing? How am I doing time-wise? Okay. So that's a small little ROV in a tank, so it's not the challenging conditions we're talking about. Here now we're looking at auto docking. So we've been funded by SFI to acquire this light work class ROV, and this is that ROV coming back into its dock fully automatically. So the robot is imaging the dock. We've a light pattern where the camera is on the dock looking at the robot. We've a structured light pattern, and the robot is imaging and aligning itself based on the structured light. In one of these cases, the dock is stationary. In the other case, the dock is heaving, because if we have permanently deployed robots on heaving offshore infrastructure, they'll be heaving up and down. And we've done both trials. Okay, time constrained in this presentation, so we have just very quick image of some of the UAV work we're doing. So we're funded by ESB to do some line surveys. We don't have much offshore wind infrastructure in Ireland, but we're trying to develop the capability so that we can do above the waterline inspection of offshore wind. Meantime, we're working with ESB, maybe do some line inspections, some fault detections with thermal imaging cameras, and another one of our support companies, Commissioner of Irish Lights, is also interested in, after every yellow warning storm or orange warning storm, they have to check every lighthouse and every navigation light around the country with a visual inspection. It obviously makes sense that rather than scrambling helicopters to do that work, if we can do it with UAVs. But we need long-range UAVs, not the little type that shut down all the airports in London and Dublin, but something that maybe has a 100-kilometre range. So we've acquired, with a Turkish-based company that has an Irish subsidiary, a UAV such as this, and we'll be flying that. So that's a test flight out in near Spanish Point. So that's some of the work we're doing. The rest is just some sliding videos over many. So rather than giving you 200 slides and keeping you here till 10 o'clock, I've just a summary of. So this is the ROV we've been supported by SFI to acquire, the official launch of it. We've used it offshore on wind energy farms in the UK, testing below the waterline. We've had a recent very successful survey cruise in January, and Gerard Dooley, one of our postdocs, was chief scientist on that survey. So some of the images from that, images of newly found World War I U-boats on the seabed, and imaging infrastructure, terminal infrastructure at the end of the gas pipelines on the Kinsale gas field. So the Kinsale gas field is coming close to end of life. That's an image of a previously surveyed a number of years ago UC42, which is again off Roach's Point. It's about 150 metres from the Kinsale gas pipeline. So once they found that there was some anomaly in the return, we did a detailed survey with our robot systems on the back of the Navy ship. And since that, because there was TNT mines still on that and close to the gas pipeline, they've encased a lot of it in effectively a concrete sarcophagus. This is the largest ever ship sunk by U-boat in the Second War, the SS Empress of Britain. She's about 2 metres short, was about 2 metres short of the Titanic. And she was broken in midsection by a torpedo. That's about 60 miles west of bloody Foreland in Donegal. We surveyed it on a return trip from further north in the Atlantic, and so we literally only got 20 minutes with the ROV flying above that, so we didn't come in close for visual survey. We've done some work in survey for Shannon Foynes Port Company and their deep water berth out in Foynes. And then here's some little video clips from the recent survey with the new ROV aboard the Celtic Explorer. So this is the gas fields off Kinsale, in the Kinsale field. So this is our 2D pilot display, where the pilot can basically choose the waypoints and choose the trajectories he wishes the ROV to follow. I don't think we haven't shown the 3D image in this video clip, and some of the live footage from the cameras, etc. Rather than, I think this is the same survey but on a newly discovered wreck, which turned out to be a World War I submarine, and is the first submarine sunk by the US Navy. So it was close to the end of the First War. So this is real-time 3D sonar imaging, and you can see the hull of the submarine, and we can see the first sight of a 10-inch gun on the deck of that submarine. And you can see the 2D display, so the planned lines. So from a low-resolution survey, we know roughly the lie of the target on the seabed, plan the lines, and then get the robot to fly down and do the high-resolution imaging with the sonar. And some of the hazards, some of the reasons we need pilots in the loop here, on a lot of these wrecks there's fishing nets strewn on them. So if we had a fully automatic survey, we'd end up getting the robot snagged in the fishing nets, the monofilament fishing nets, etc. So some other testing then in the local dock with a small little inspection ROV. So on this little ROV we have the full flight capability of the larger ROV, but we cannot have the full manipulators and intervention capability. So that's testing it again in Portroe in the Slate Quarry. This is testing automatic fault accommodation, so turning on and off different thrusters, isolating faults, and seeing can we still hold station in wave environment in the National Ocean Testing Centre down in, which is funded by Mare, in UCC in Ringaskiddy. That's the same robot in the lake. This is working with scientists and marine biologists who are funded in this national programme from NUI Galway, who are interested to see if some of these wrecks, and that's a scatter plot of the wrecks around the Irish coast and in the Irish seabed territories. So that's a single wreck, which is about somewhere here, and in much shallower water than they thought before they found these cold water corals. So they're growing in protected areas on that wreck. So that may influence natural habitat protection, etc. And a lot of these wrecks and man-made reefs, which become effectively, over time, they convert into natural reefs, spawning grounds for many fish species. This is, do you remember the image we had of the submarine bar? Well, this is that scene. So this is the bottom of the Portroe Slate Quarry, and we're just flying in for a promotional video. So TV, so that the divers can watch TV when they're submerged, the mannequin and the large ROV in the background. So as you can imagine, some of this work is fun. But doing that was acquired in October, so there's actually surface temperatures sort of frosty and sub-zero. And that's an image of the Portroe Slate Quarry, the flooded quarry, and inside the control cabin. Okay, I think we're okay. This is the inspection work with our robot, as it turned out, in relatively clement weather. So we weren't as reliant on all our developed and sophisticated target flight control systems. But what we're trying to do is do the same work that we did in this survey for a commercial client in more and more challenging conditions. So open the operational windows for servicing these offshore infrastructures. So just some images with videos. So dual Orion, so we've 2 Orion manipulators on the front of the robot. We don't need the full inverse kinematic engine. because of the static conditions. So this is marine growth on the underwater structure, probing the depth of marine growth, etc., and maybe figuring out does it need to be pressure jetted off to clean and maybe inspect wells, etc. So you wouldn't know looking at that you're actually looking at steel structure submarine beneath offshore wind. Looking at the cables, the flexible risers, the J tubes where the cables come into the towers and the structures, they all need to be inspected. What's this one? Anode. So a lot of the steel structures subsea are protected with sacrificial anodes, zinc anodes which slowly dissolve into the ocean and protect the steel. So we need to check the integrity of those, that they're not insulated with a layer of bio film, that they're still effectively operating and saving the steel, and they need to be replaced periodically. This is jetting, so removing the biological growth from the anode so that we can probe them. And that's our robot on the back of the service vessel in this case. So some of our robots, ones we've built ourselves. We started in the AUV world with these two vehicles, then built ROV lattice, because a lot of the commercial work for robots is close quarters intervention work, which you cannot do with fully autonomous vehicles. So we've been working very much in the smart controls on robots. This is a small inspection ROV, and this is the large intervention ROV in a launch and recovery system, where we launched a full garage system with the ROV inside. Once we're subsea, we fly the robot out of the garage. We've also acquired this UAV system, which has got range capability for endurance of 7 hours and range capability maybe 100 kilometers and more. And then this is a NATO-funded project where we're working on Science for Peace project. We're not developing weapon systems, to be able to deliver UAVs if there's some marine incident, like an ecological incident, with a multi-copter, can we deliver that in rapid response. But this is using liquid fuel engines rather than the LiPo batteries. With the LiPo batteries we typically get half-hour endurance. We won't get any range with half-hour endurance. That's me. So we're sunset. So any questions?